Hey everyone, and welcome to your custom deep dive. Today we're diving headfirst into particle physics.
Absolutely.
But don't worry, we're going to make sure it's exhilarating and not jargon-filled.
Yeah, we're going to unravel the mysteries of the universe one particle at a time.
That's right. So we're taking a closer look at this research paper, High Energy Lepton Colliders as the Ultimate Higgs Microscopes.
Okay.
Have you ever wondered how scientists actually see particles that are billions of times smaller than an atom?
Right.
It's like trying to find a grain of sand in the entire Sahara Desert.
Yeah.
But get this research is about machines that are essentially like super-powered microscopes.
Yes.
They allow us to zoom in on these tiny particles with incredible precision.
These machines are known as high-energy lepton colliders, like the ILC and CLIC.
And they're powerful too.
Yeah, they are.
Imagine the energy of a mosquito flying full speed.
Okay.
Now squeeze that energy into a space 1 trillion times smaller.
Wow.
That's the kind of power these colliders are packing. They can smash particles together with energies up to 3 trillion electron volts,
Wow.
which is 3,000 times more powerful than the Large Hadron Collider.
That's really remarkable.
Yeah, the Large Hadron Collider discovered the Higgs boson back in 2012.
That's right.
But these new colliders will allow us to study it in ways we never thought possible.
It's like we've discovered a new continent.
Yeah.
And now we're building high-speed trains to explore it.
Exactly. But here's the thing. Even before these incredible machines are built, this research is already giving us a glimpse into the future of physics.
Yes, it's based on the legacy of a previous generation collider called LEP.
Okay.
Now, LEP had a much lower energy level, but surprisingly, it could still hint at particles and forces at energies way beyond what it could directly produce.
Interesting.
It's like getting a sneak peek into a hidden room through a tiny crack in the wall.
So what did LEP see?
Well, LEP's precise measurements at a specific energy level allowed physicists to indirectly probe energy scales up to a few TeV. To put that into perspective, imagine being able to study the afterglow of the Big Bang, just fractions of a second after it happened. That's the kind of energy scale we're talking about.
Wow.
And it could completely change our understanding of how the universe formed.
Yeah.
And the research suggests that ILC and CLIC could explore scales up to tens of TeV using similar principles.
Wow. It's like getting a front row seat to the birth of the universe.
Exactly.
Okay, so we're talking about mind-blowing energy levels here, but how do we actually make sense of all this information?
Right.
This is where the researchers get into some pretty fascinating territory.
Okay.
They focus on 3 key effects they call leptonic high-energy primaries.
Okay.
Now, don't let the name intimidate you. Think of these effects as clues, like fingerprints at a crime scene.
Right.
They become super important at these high energies and can help us understand the Higgs boson in ways we've never been able to before.
That's a great analogy.
So we're not just smashing things together randomly. We're carefully analyzing the debris, the patterns, the whispers, to understand what happened during those fractions of a second after the Big Bang.
Precisely. And the beauty of this research is that it provides a way to cut through the noise and focus on these crucial whispers. It's really like being a detective at a cosmic crime scene. We're looking for any tiny clue that could help us piece together the story of the early universe.
And these leptonic high-energy primaries are like finding that rare type of mud on the suspect's shoe.
Exactly.
Yeah.
They tell us something very specific happened, even if we don't have the whole picture yet.
Okay.
For instance, the researchers looked at how these primaries show up when a Higgs boson is produced along with another particle called a Z boson.
Okay, pause right there. I know we said no jargon, but I think we need a quick explanation for our listeners.
Sure.
What's a Z boson in this detective story?
Good point. Think of the Z boson as the messenger for one of the universe's fundamental forces, the weak force.
Okay.
It's like how a letter carrier delivers messages. The Z boson carries the influence of the weak force between particles.
So this process that the researchers simulated, it's basically watching how the Higgs, the mass giver of the universe, interacts with this force messenger. That's wild.
It is, and they call this process Higgs-Strahlung.
Higgs-Strahlung.
Yeah, don't let the name throw you off. It's just a fancy way of saying these two particles are produced together.
Higgs-Strahlung has a nice ring to it, though. But they didn't just stop with just one process, did they?
Not at all. They also simulated what happens when 2 Z bosons collide head-on and produce a Higgs boson.
Okay.
It's a process called Z boson fusion.
So two force messengers crashing into each other and out pops a Higgs boson. It's like some kind of subatomic magic show.
It's pretty amazing, and here's where it gets really interesting. The same leptonic high-energy primaries play a crucial role in both of these processes, even though they seem quite different on the surface.
So it's like finding that same rare type of mud at two seemingly unrelated crime scenes.
Precisely.
Must be a crucial clue.
This points to a deeper connection between these processes governed by fundamental physics principles.
Okay.
It's like discovering a hidden tunnel that connects those two crime scenes.
Okay, I'm on the edge of my seat. What did these simulations actually show? Could ILC and CLIC really detect these leptonic high-energy primaries and unlock these secrets?
Here's the exciting part. The simulations show that ILC and CLIC could be incredibly precise, like orders of magnitude better than previous experiments like LEP.
Wow.
And get this, they could even surpass the projected sensitivity of a major upgrade to the Large Hadron Collider.
Wow, so we're talking about a whole new level of precision here, like trading in our magnifying glass for a high-powered electron microscope in our detective work.
Exactly. And with that level of precision, we could potentially see things that were previously hidden from view.
Yeah.
It's like suddenly being able to see the faintest footprints at a crime scene, footprints we didn't even know were there before.
So what does this all mean for our understanding of the universe? Are we talking about discovering new particles, new forces, maybe even a whole new understanding of physics? It's like we've been working with these blurry Polaroids, and now we're finally getting our hands on, high-definition images.
Yeah, and that's what's so exciting. This research isn't just about confirming what we already know. It's about cracking open the door to the unknown.
Right.
We could be talking about discovering a whole zoo of new particles.
Yeah.
Like finding out that there are species of animals we never even imagined existed.
It's like we've only explored this tiny island in this vast ocean of possibilities.
Exactly.
What kind of strange and wonderful creatures might be lurking in those uncharted waters? Could we even find evidence of entirely new forces, forces beyond the ones we already know about?
That's the beauty of science. We don't know the answers until we look. But what makes this research even more compelling is that it provides this direct link
Okay.
between those leptonic high-energy primaries, our tiny clues, and things we can actually measure. Things like, the strength of particle interactions, the
Wow.
energy they carry.
Okay.
These are the telltale signs that can point us in the right direction.
So it's like those faint footprints leading us to a hidden treasure chest, and inside, who knows what we'll find.
Exactly.
Yeah.
But carefully measuring these quantities at ILC and CLIC, we can either confirm our current theories or even more excitingly discover something completely unexpected.
It's both exhilarating and a little bit scary to think about, isn't it? We could be on the verge of rewriting physics as we know it.
It's the ultimate detective story, and we're
Yes.
just starting to unravel the clues.
Well, there you have it, folks. Your crash course on the future of particle physics. Who knew that smashing tiny particles together at unimaginable speeds could be so insightful?
It's really a testament to the power of human curiosity and ingenuity.
Yeah.
We never stop pushing the boundaries of what we know, and that's what makes this field so captivating.
This deep dive has certainly left me with a lot to ponder. What about you? What are your thoughts on these high-energy particle collisions and the secrets they might unlock? Let us know. We'd love to hear from you. Until next time, keep exploring, keep questioning, and keep looking for those whispers from the universe.